Washington State University. Go Cougs!
Welcome back to the class on behavior analysis from mobile sensor data. In this course segment, we will talk about activity learning, specifically on the task of activity recognition. Recall that in this discussion of activity learning, we first talked about how to extract a feature vector from the collected sensor data that was collected using a mobile device such as a phone or a watch or other wearable. And in this segment, we will talk about how to automatically recognize the activity that is being performed given the values found in that feature vector. This is the app that you learned how to design earlier in this course and the corresponding sensors that were monitored. It is that sensor data that we will be using to automatically recognize activities. This is the sensor data that we used in the previous video from which we extracted the feature vector shown here. This is a window that represents 5 seconds of collected sensor data, and we extracted from this entire sequence of information a variety of statistical, relational, signal processing, and locational features. This feature vector is only part of what could be a very long vector. Each vector represents a data point. The task of activity recognition is to map this data point, or the feature vector V, onto an activity label from a set A of possible activity classes. Using a mobile device, such activity classes might include sleep, relax, work, eat, exercise, drive, walk, bicycle, or in some cases, there might be collected data that does not fall into a predefined activity category, and it could be labeled as other. In our particular case, with the 5 seconds of data that we showed and the corresponding feature vector V, ideally we would map this onto the activity label EAT, because this data was collected using the activity learning app that we showed earlier in the class, and the user actually labeled this activity as EAT. You recall that the person was at a location corresponding to Starbucks. The phone was more or less at rest. And from the time of day, the location, and other information, ideally we should be able to infer that this is the activity they are performing. These are the steps that are involved in activity recognition from sensor data, and some of this information was also discussed in the companion course, Behavior Analysis from Ambient Sensor Data. Using the app that you designed, you can accomplish the first step, which is to collect sensor data from a mobile device while an individual performs routine activities. In this case, the data that would be collected would correspond to the sensor information that's available on your phone. It could also include app-specific information and additional information not collected in the app that you wrote, such as video from the phone, audio, and other sources of external information. Once the data is collected, it's time-stamped, so the next step is to pre-process the data by removing any noise, and also segmenting the data corresponding to the portion of time that you want to label with a specific activity and any context that is useful to help determine what activity is being performed at that time. Recall in the previous segment of the course, we discussed ways to segment the data either through segmentation if we know where the activity begins and ends, or by using a sliding window through the data and looking at an activity label that corresponds to that particular sequence of information. In addition to segmenting the data one window per activity, if we know where the activities begin and end, we can also use techniques such as change point detection to automatically determine when the nature of the data statistically changes enough so that it warrants ending the segment at that point and starting a new one after that change, because a change point indicates that there's been a change in the process that is generating the observed data. The next step is feature extraction, which we discussed in the previous video. And finally, once a feature is extracted that represents a particular data point, the last step is to use a supervised learning algorithm to map that data point onto an activity label. There are many classifiers that could be used for this task of learning a mapping from a data point to a label. Here are some that are available, many of which can be accessed using scikit, which is a Python-based library. All of these are effective. We have found random forests to be particularly accurate on this type of data. There are a number of activity recognition challenges that need to be considered when performing activity recognition from mobile sensor data. One is the very likely situation in which you have a skewed distribution of data points among your available activity classes, either because people spend more time in one activity than others. For example, more time is spent in sleep typically than in the process of entering or leaving a home, or because they don't provide as many labeled data points for one activity as another. Again, individuals might spend more time answering queries for an activity such as eat or cook than they would for sleep, during which time they do not want to be interrupted. Another reason for such a skewed class distribution is that typically we only want to monitor a fixed set of predefined activities such as those listed here. The ones listed here, though, don't make up all of an individual's routine. In fact, this distribution comes from an actual set of sensor data that was collected for an individual over a period of several months. And in this case, the predefined activities make up about half of the data, and the rest is put into an other category. The problem with having a skewed class distribution is that classifiers which are attempting to optimize accuracy will tend to put many data points into the large category that actually belong into the smaller activity categories. There are some approaches to deal with this challenge. One is to use a sampling-based pre-processing step in which data points from the majority classes are actually removed in order to make the distributions more uniform, or data points are artificially created that are quite similar or close to the smaller classes in order to, again, make the distribution more uniform. Another approach is cost-sensitive learning, in which data points are weighted based on their importance, and then when the classifier learns a mapping from the data point to the activity category, those categories that are treated as more important, or the data points that are weighted more heavily, will influence the classifier to focus more intently on that data point or category, which has the same net effect as having more training data available in that category, although it will be repetitive information. While cost-sensitive learning can be used to emphasize a particular data point or class, it can also be used to essentially balance the activity distribution by weighting activity categories inversely proportional to the amount of training data that is available in that particular category. Also, when performing activity recognition from mobile sensor data, keep in mind that the data is not independently and identically distributed. It is non-IID. This means that each data point, which is our feature vector, is not independent of the data that comes before it in the sequence. That has an implication for how we evaluate activity recognition algorithms. For example, if we provide some of the data to train the model and other data to test it, and those data points are quite close to each other in time, we may be biasing our activity recognition evaluation. On the other hand, if we train our model based on one set of data and test it on another set of data that is far removed in time, we might run into another problem, which is concept drift. Concept drift indicates that the underlying data and mapping from data to activity label has changed over that period of time between training and testing, possibly due to the fact that the mobile device user has actually changed their routine and the way in which they perform these activities. That would result in lowering the accuracy of the activity recognition algorithm, while having training and testing data very close together in time may artificially increase the accuracy of the activity recognition algorithm. Here are some possible measures that can be used to evaluate activity recognition. The one that I've been mentioning is accuracy. In this case, we would train a model on some of the data, leave some data out for testing, and on the testing data, accuracy would be evaluated as the number of data points that were correctly classified divided by the total number of data points that were labeled with an activity. However, because of the class distribution or the importance of recognizing a specific activity class, you might also consider measures such as sensitivity, which is the true positive rate, the number of correctly classified activities in a particular category divided by the true positive plus false negative classifications for that category. Specificity would also be calculated based on a category or activity class, and this is true negative divided by true negative plus false positive for that particular activity class. A common measure used in cases where you have an imbalanced class distribution is G-mean, which is the square root of the product of sensitivity and specificity. And this could be calculated per activity category, or it could be averaged over all activity categories, depending on what you want to try to show for the activity model. Another consideration is how to select the data for training and testing. One popular technique for separating the data into training and testing is cross-validation, in which the entire set of data is partitioned into K subsamples. K minus 1 of the subsamples are used for training, and then the K sample is used for testing. The whole process repeated K times so that every partition has a chance to serve as the test subsample once. When doing this, however, if we treat all of the data points equally, all of our feature vectors, we run into the risk of finding neighboring points in time being used, one as training and one as testing, which might bias the results. So an alternative approach is to partition the data in time using all of the data before a particular time point as training and data after the time point as testing. If we want to determine the generalizability of our model, we might also consider a leave one subject out evaluation. If we have n subjects or individuals from whom we have collected data and have made sure to have labels, we can train the data on n-1 of those subjects and test it on the nth subject. And as with cross-validation, we can repeat this process so that every subject is treated as a test case once, averaging the results so that we can see how well our activity models trained on one individual or set of individuals can accurately label activities for another on whom the model has not been trained.